It is well known that for a system with completely random phase fluctuations in 2 or 3 dimensions, the density probability distribution is always exponential. This unique behavior, for example, can be observed for a light wave having phase fluctuations with 2 freedoms. In this work, we will give the first experimental demonstration of this exponential density probability distribution with math waves. In our experiment, a one-dimensional optical lattice with periodic potentials was applied along the axis direction of cigar-shaped condensate. After a time of free expansion, the atomic density was recorded by our CCD camera. From the atomic density, we extract the density probability distribution and make a compare with the exponentially decaying curve. We found that the density probability distribution matches the exponential shape when lattice depth is high enough. For the 1D optical lattice system, the Bose gas in each lattice well becomes quasi-2D, and the quasi-2D gas should undergo the BKT transition at the critical temperature. About this critical temperature, the unbinding of bond vortices will lead to strong spatial phase fluctuations within the single-step condensate. Of course, there also exists another kind of phase fluctuations, that is, the relative phase fluctuations between the different lattice wells. In the phase diagram, the BKT transition line divides the quantum critical region into 2 parts, the type 1 and type 2. We focus on type 1 QC region, taking into account the intersite and the intrasite phase fluctuations. We calculated the density probability distribution and found that it does follow an exponential rule. In superfluid region, or type 2 QC region, only intersite phase fluctuations exist, and the exponential rule is not obeyed according to our theoretical model. Our experiments have justified that the exponential rule is varied once the system enters type 1 quantum critical region. We also numerically simulated the density distribution in 3 regions. The results for superfluid and the type 1 QC regions are in good agreement with the experiment. In summary, we have demonstrated an exponential density probability distribution of ultracold quantum critical Bose gases in a one-dimensional optical lattice by experiment. We have also given a simple theoretical model to explain the observed universal behavior. Thank you for your attention.